Good morning once again. I hope you all had a good weekend. And kind of winding down the semester. Still a couple of more things I need to go over with you guys before we complete the course. If you have not already, please watch Friday's lecture. So Friday I recorded a live lecture. 3 of you guys came, so thank you for coming. And you guys don't have to watch it unless it's a review. But the others, make sure you watch it because I'm just going to move on and move ahead. And I think that's it for now. I'll email you any due dates with regards to the lab notebook and lab reports and so on and so forth. So we are continuing our discussion on Lewis structures. Oh, one more announcement I need to make. I just reminded myself, sorry. Wednesday, I believe, is a holiday, Veterans Day. So Friday, we will have a lecture here. So it's going to be 14. The attendance will be capped at 14. So I think no one really shows up to these. But if you want to come to Friday's lecture, that possibility is available for you. So make sure you come to Friday's lecture. If not, at least watch the video, right? So watch the recording of Friday's lecture if you're not planning to come to actually Friday's lecture. And then Wednesday, Wednesday I guess would be your catch-up day and also observing Veterans Day. So let us continue now. Let us continue with talking about Lewis structures. Today is the 9th. Let this focus. All right. All right, today I want to talk to you guys about a couple of things here. Before I actually talk about resonance, let's just practice one more type of Lewis structure. Just practice one more. How about we do this one here, SF6. Okay, this molecule is called sulfur hexafluoride. Okay, if you have not seen Friday's lecture, this may seem somewhat foreign to you. So definitely watch Friday's lecture, last Friday's, to get a review. So anyways, we're going to draw the Lewis structure of sulfur hexafluoride. Right, so first thing is we're going to determine our valence count. Okay, so sulfur is happy at what number? 4. No. It's going to be happy at... we'll look at the periodic table. Where is sulfur happy at? It's at the same group as oxygen. So oxygen is happy at 6. Right? So sulfur is going to be happy at 6. All right. So sulfur is happy at 6. What is fluorine happy at? All the amino acids. All the halogens. What are all the halogens happy at? 7 is right. Very good. Okay, 7. Thank you, Adriana. Okay. And how many do we have? We have 6, so 42. Okay, by the way, if you want to know why sulfur is happy at 6, okay, we can do this. Carbon loves 4. Carbon loves 4. Nitrogen loves 5. Oxygen is 6. So sulfur will be 6, fluorine and all the halogens are 7, fluorine and all the halogens are 7, and then the noble gases are going to be happy at 8. Okay. So 4, 5, 6, 7, 8. Right, so our goal here is to get 48 valence electrons around sulfur hexafluoride. So what is our central atom? It's not fluorine because we don't know which of the 6 fluorines is going to be central. So best to go with sulfur as your central. And then we're going to attach 6 fluorines, the substituents. Substituents is the name of the term for the outer atom. All right, so 1, 2, 3, 4, we'll just do here 5, 6. Okay, so we need to get 48 valence electrons. So I want you guys to count with me, okay, as we're going to do till now, till the last day of the class. So ready? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, we need to get 48. 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36, 37, 38, 39, 40, 41, 42, 43, 44, 45, 46, 47, 48. Okay, now I got all my 48 valence electrons accounted for. Okay, again, this is just a 1D structure. Okay, on Friday we will, I hope, to show you some of these in 3D when I bring out the big Coke bottles. Okay, on Friday. We'll try to show you the 3D aspect of these molecules. All right, the important thing here is formal charge and octet rule, out of which I want to tell you guys that formal charge is going to be more important. All right, so let's do sulfur formal charge. Okay, I'm talking about sulfur here. Okay, ready? 1, 2, 3, 4, 5, 6. What is sulfur happy at? 6. 6 minus 6 is 0. Formal charge on that sulfur is 0. Okay, now let's do the octet rule. In the octet rule, I want to tell you guys, and on the test, on Canvas test, okay, or whatever future chemistry classes, octet rule, you count everything individually. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, so the octet rule for sulfur is 12. We will call that an expanded octet. Okay, we will call that an expanded octet. So that's okay, right? So remember, there's a lot of fudging with the octet rule. Okay, you're getting your formal charge minimized is the most important thing. Expanded octet is totally fine. Now we're going to do the same thing, you guys, for the fluorine. I'm just going to pick this fluorine, realizing they're all the same. Okay, so the formal charge for this fluorine, formal charge. Okay, ready? Here we go. 1, 2, 3, 4, 5, 6, 7. What is fluorine happy at? 7. What's 7 minus 7? 0. Okay. Octet rule for fluorine. All right, count everything individually. 1, 2, 3, 4, 5, 6, 7, and 8. Okay, so it's not an expanded octet, even if it's not. So it's okay for the expanded. It's okay for the octet rule. Right, so total charge is 0. If I were to give you this on the exam, you'll see there's no charge, 0, so everything is good. All right, so the next question here is the molecular geometry. Okay, the molecular geometry. What does this look like in 3D? Again, on Friday, I'll bring, I don't know how you'll watch it if you watch it on video, but we'll see what some of these look like. Okay. Molecular geometry, central atom, 1, 2, 3, 4, 5, 6. So 6 bonding, 0 lone pair. Okay, 6 bonding, 0 lone pair. So here you want to use table 10.1. In your textbook, you can use 10.1 and 10.2 on your exam. Why am I saying 10.1 instead of 10.2? Because here, okay, the central atom has no lone pairs. Okay, so 6 bonds, 0 lone pairs. 1, 2, 3, 4, 5, 6. 6 bonds, 0 lone pairs. What's 6 bonds, 0 lone pairs? Okay, that is going to be 6 bonds. 6 bonds. 0 lone pairs. The molecular geometry is going to be octahedral. Okay? Octahedral. And in fact, this is the example of an octahedral molecule. So the molecular geometry, how this would look like in 3-dimensional space, is octahedral. All right, octahedral. So make sure you utilize 10.1 and 10.2 for your exams. And I'll give you more information on your exam next week. I'm still in the process of making it. So the molecular geometry is octahedral. Okay. So how will we draw this in 3-dimensional space? Okay, well, this kind of tells you how you would draw it. Okay. So here we would have the sulfur atom. We have this fluorine and this fluorine up and above the plane of the piece of paper. Okay, we can draw what's called a wedge. Almost looks like a wedge for the wedge of the door. So this means it's coming towards you guys. Okay, it's coming towards you guys. Coming right towards you, Joshua or Kimberly. It's right sticking out, okay, above the paper. This specific bond is called wedge. And then the dash means it's going away from you. Okay, it's going down the paper, it's going away from us. And we'll call that it's just a way to try to depict something 3D into 1D. That's all. So this is a dash bond and then a wedge bond. Okay, wedge is coming out of the paper. You may wonder why the geometry of this is octahedral. If I take the center of every atom in orange, okay, and I connect it, and again, your professor, your teacher is not Picasso, so what you actually see here is it's sort of like a tetrahedron on top and a tetrahedron on the bottom. I don't know how good you guys are in seeing things in 3D. Some of you have it, some of you don't. I do not have it, but it's like looking down at a pyramid. Okay, and the octahedral comes from 1, 2, 3, 4, 5, 6, 7, 8. Okay, so again, we're just trying to draw things in 3D on a flat piece of paper. Huh? At the top, you're looking down. Pretend you're on a helicopter. You're looking down. You're going to see the sulfur, and then, kind of like in a pyramid, you're going to see the fluorines. right, molecular geometry. The next thing on our agenda for this molecule is polarity. This will be very important when we talk about whether the molecule is polar and nonpolar in the General Chemistry 2 class. So the idea is this. Okay, you see fluorine is going to pull this way. The electronegative elements, fluorine, oxygen, halogens, nitrogen. Fluorine is going to pull this way, making it partial negative. This is going to be canceled out by the pull of the fluorine in the opposite direction. This fluorine down, okay, this is 1D. This fluorine down is pulling this way. This fluorine up is pulling the opposite way. Okay. This fluorine here is pulling this way, right, Adriana, right? And then this fluorine on the other side is pulling the opposite way. Okay, so fluorine down is being canceled by the fluorine pulling up. Fluorine pulling to the left is canceled by the fluorine pulling to the right. Fluorine pulling away is canceled by the fluorine pulling the opposite way. All the movements cancel each other, so this is a nonpolar molecule. Okay, nonpolar molecule. Right, our last thing we need to think about here is hybridization. That's the last thing on our plate for this molecule here. So for hybridization purposes, we are mixing orbitals. All right, 6 bonds and 0 lone pairs. What's 6 plus 0? It's 6. So we're going to take 1 from S. How many are there from P? There's 3 from P. Remember, P has 3 slots. Well, 3 plus 1 is 4. I need 6. Where will I go next? D. So 1, 2, 3, 4, 5, 6. So this is an sp3d2 hybridized sulfur. sp3d2 hybridized sulfur. And that completes the SF6. Okay, let's do one more. Well, we're going to keep on doing this till the last day of class. So this is not an example of resonance, by the way. So resonance, need a topic. So topic we will go over today is resonance, but sulfur hexafluoride is not an example of resonance. All right, example number 2 here is xenon tetrafluoride. Okay, this is called xenon tetrafluoride. All right, so what is xenon happy at? And what are the noble gases happy at? Okay, I don't have my periodic table, but 8. Okay, what is fluorine happy at, as well as all the halogens? Okay, but you see we got 4 of them, so 7 times 4 is 28. So we need to get 36 valence electrons around the XeF4 xenon tetrafluoride molecule. Okay, let's make xenon our central atom because we have no idea which of the 4 fluorines is going to be central. So let's make xenon our central atom. Let's attach our, again, this is the 1D. Let's attach our fluorines in there. we ready now? Okay, we need to get 36 valence electrons. Okay, 1, 2, 3, 4, 5, 6, 7, 8. All right, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26. We good with me? 27, 28, 29, 30, 31, 32. But I need 36. Okay, 32. Where will 33, 34 electron and 35, 36 electron go? They have to go to the xenon. Very, very good. So 33, 34, 35, 36. Okay, excellent. They go back to the central atom. You can't have a double bond with the fluorine because that's going to mess up your formal charge. All right, let's look at the formal charge of fluorine. Let's look at the formal charge and octet rule of fluorine here. All right, so ready? Okay, count with me. 1, 2, 3, 4, 5, 6, 7. What is fluorine happy at? 7. 7 minus 7 is 0. Okay, very good. Octet rule for this fluorine. Ready? You count everything individually. So count with me, you guys. 1, 2, 3, 4, 5, 6, 7, 8. Okay, very good. All right, the xenon formal charge. Okay, ready? 1, 2, 3, 4, 5, 6, 7, 8. What is xenon happy at? 8. What's 8 minus 8? 0. Okay, the octet rule for xenon. Count everything individually. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, we call that an expanded octet. It's totally okay. Okay.
With an expanded octet, is that always going to be something that has more than 8?
Yes, but there are some that don't get an octet. Hydrogen, the octet is 2. Okay, aluminum, the octet is 6. Okay, so if you can get an octet, good, but some of these central atoms, the central atoms will take the expanded octet. Okay, So the expanded octet is okay for this example. Because you see, you want to always get your formal charge. See, the formal charge is 0 here, and the problem, there is no charge, it's 0. All right, the next question here is polarity. No, the next question is the molecular geometry, sorry. So you need to ask yourselves how many bonds and how many lone pairs. Okay, so how many bonds do we have here? 4 bonds and how many lone pairs? 4 bonds and 2 lone pairs. 4 bonds and 2 lone pairs. So here you want to use the table for the center atom with lone pairs. Okay, the center atom with lone pairs. All right, so here the difference here, the central atom has 1 or more lone pairs. Okay, so make sure you bring this to the exam, and I'll have copies on Canvas. So, what is it? 4 bonds, 2 lone pairs. So here you're going to go number of bonding pairs. Okay, it's not 2, it's not 3, it's 4 bonds and 1 lone pair is not right. Okay, I want you to go all the way down. 4 bonds and 2 lone pairs. Number of lone pairs is 4. I'm sorry, number of bonding pairs is 4. Number of lone pairs is 2. Everyone see that? Okay, 4 bonds, 2 lone pairs. What's the geometry? Okay, geometry is going to be square planar. Okay, and in fact, that's the example they give you, square planar. So the molecular geometry of XeF4 is square planar. Okay, so all of these things. Anybody here know structural biology? That's where I got my PhD in a structural biology lab. So we don't look at structure. We look at structures, but we look at them in proteins, like more complicated than these molecules. Anyways, the three-dimensional shape of this molecule XeF4 is square planar. So square planar. All these structures have a three-dimensional shape and geometry. The next challenge is to try to figure out how to draw this in three-dimensional space. So here's one way you can do it. Again, there's more than one answer. So you can have the XeFe I'll have them come the back. Okay, so it's coming away from you guys. And then this fluorine is coming above. Again, please realize there's more than one way to draw this in 3 dimensions. And I'll have the lone pairs come on the piece of paper. Another thing I can do, if these 2 fluorines are coming towards you, if I do a 90-degree flip, okay, let's say I flip this 90 degrees, you really have to think 3-dimensionally now. If this is coming towards you, if I flip it, okay, this fluorine and this fluorine, if I flip it, it's coming towards you. If I flip it 90 degrees, then they're going to be on the plane of the paper. And this pair of electrons will actually come towards you. Again, 90-degree flip. And this pair of electrons, again, 90-degree flip. Okay, electron come towards you, Harper. This pair of electrons goes in the back. So there's many ways to draw something that's 3D, okay, into a 1D piece of paper. Okay, it's a little bit neat for those of you that have that interest. Okay. All right, so the geometry is square planar. The next question is the polarity. Okay, what do you guys think? Is this polar or non-polar? Okay, any guesses? The fluorine is going to pull. Okay, who's counterbalancing that? This fluorine. This fluorine is going to pull this way. Okay, who's counterbalancing that? That one. Okay, this pair of electrons is pulling in its own directionality. And who's counterbalancing that? This one here. Okay, so all the pulls are being canceled out. All the pulls are being canceled out. So this actually is a nonpolar molecule. Because the pull is being canceled. Okay, we pull at the same strength, so we wind up, not left or not right, but right at neutral 0. So this is a nonpolar molecule. All right, 4 bonds and 2 lone pairs. How will we accommodate that? 4 plus 2 is 6, right? So we're going to take 1s. P has 3 slots available. And then how many will we take from D? 3 plus 1 is 4. Okay, how many more do we need to get to 6? We need 2. Okay, so this is an sp3d2 hybridized xenon. Okay, this is our hybridization. All right, now let's talk about resonance. On Friday, we'll go over more examples. Here on out is just mostly some examples here. I want to expose you guys to resonance. Okay, so resonance structures are basically hybrid structures. Okay, so there's more than one form, and they're all equivalent. Oops, sorry, more than one form. Okay, more than one form, and they're all equivalent. Example of this, remember your flashcards? One example of this is the carbonate ion. Can you remember from your flashcards? This was part of your flashcards. Okay, and it's a good example of resonance. Okay, so let's draw this. Carbon is happy at 4. Carbon loves 4. Oxygen is happy at 6, but we got 3 of these oxygens, so 6 times 3 is 18. Okay, and minus 2, what does the minus 2 mean? Okay, it means we gained 2 electrons, is it not so? So 4 plus 18 is 22. 22 plus 2 is 24. Okay, so our goal is to get 24 valence electrons around the carbonate ion. Let's make carbon our center atom because we don't know which of the 3 which of the 3 oxygens, 1, 2, or 3 is center. So yeah, I'm going to do carbon and then 3 oxygens. By the way, carbon loves what? No matter what. Okay, you have to know this. Carbon loves 4. Okay, loves 4. All right. So how will I get to 4? When I have 3, extra 2. How will I get to 4 here? Not a single bond, but a double bond. Okay. So that's how you'll get to 4. All right. Right. 1, 2, 3, 4. Okay, so carbon loves 4.
Doesn't matter which one it goes to.
That's the idea behind resonance. Okay. I think, yeah. And all right, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. Okay. All right, let's do before I answer Joshua's question, let's do our formal charge for the carbon. Obviously, it's ahead of me. So formal charge of this carbon. 1, 2, 3, 4. What is carbon happy at? 4. What's 4 minus 4? 0. Okay, the octet rule for this carbon, count everything. 1, 2, everything is shared. It gets counted as 1. So this carbon and this oxygen share electrons, but we're going to count them for carbon. 1, 2, 3, 4, 5, 6, 7, 8. Okay, octet rule is good. All right, how about the octet rule for this oxygen? octet rule for this oxygen here. One. Okay, ready? 1, 2, 3, 4, 5, 6, 7, 8. Octet rule satisfied. What about formal charge? 1, 2, 3, 4, 5, 6. What's the formal charge of this oxygen? 0. All right, this oxygen and that oxygen are very different. Why? Because this one has a double bond. This top one has a single bond, so we got to do it for this oxygen. Formal charge, 1, 2, 3, 4, 5, 6, 7. What is oxygen happy at? 6 minus 7 is minus 1. So this oxygen has a minus formal charge. Okay, you want me to do it for this one? All right, formal charge for this oxygen, 1, 2, 3, 4, 5, 6, 7. What is oxygen happy at? 6. What's 6 minus 7? Negative 1. So this one has a minus 1 formal charge. Okay, what about the octet rule? Okay, 1, 2, 3, 4, 5, 6, 7, 8. Octet rule is satisfied. All right, so minus 1 here, a total of minus 2. Well, you know, that tells you where the minus 2 comes from. Okay. All right, coming back to Joshua's question, okay, he has a pretty astute insight. Doesn't matter which way the double bond goes. So I just randomly chose the double bond this way. Okay, but it can also go up top, right? So that's one structure. So to make it go up top, okay, you can put this pair of electrons here, kick out that pair of electrons there. Right? Because I want the double bond on top. So I'm gonna move this pair of electrons here, kick that pair of electrons to the oxygen, and now this is what I have. An oxygen, okay, with the carbon. Here's my double bond, and I left that oxygen alone on the right hand side. Okay, formal charge, right? 1, 2, 3, 4, 5, 6, 7. Oxygen happy at 6. 6 minus 7 is minus 1. And this also, oxygen here on the rightmost will have a formal charge of minus 1. Okay, don't forget there's 2 lone pairs of electrons here. Okay, because I moved one of those to make the double bond. And that's one resonance structure. Okay, what's the last one? Double bond to the right. Very good. So to do that, double bond to the right, I'll push this one here and kick this one out there, and that will get my double bond to the right. And that looks to be all the resonance structures of the carbonate ion. Don't forget to put your open and closed your brackets. Okay, so what's pretty powerful about resonance structures is that you see the double bond. Okay, the double bond is sort of shared across all oxygen atoms. You see the 2 minus charges, minus 1 here, minus 1 here, minus and a minus, a minus and a minus. They are shared equally. Okay, so we call this delocalized in the chemistry field. Delocalization or delocalized, that is to say the minus charge is really equally shared across all 3 oxygen atoms. Okay, it's like zzz, it's not like on one oxygen atom, but it's like a bee buzzing, and it's buzzing equally, and happily across all three. Instead of having one oxygen atom where that negative charge is, you can share it across all three oxygen atoms. So that is an example of resonance. Okay, it's not like this one is better than that one or that one is better than this one. They are all three shared. Okay, all three. On a test, I'd want you to draw all three because they're all three are equal. Yeah.
Would they all three have the same properties, or would it change
Yes.
based on the...
Yes, they all have the same properties. One of the properties is stability. These are very stable. Okay, because of the resonance stabilization. So you can have the carbonate, you can have a bottle of carbonate, okay? Because they're stable, it's not very reactive. All right. Let's do another example of resonance. How about nitrate? Okay, remember from your flashcards the nitrate ion? Okay, these nitrates are found in a lot of food additives. Right, so let me draw the structure of this for you guys. Okay, so what is nitrogen happy at? 5 is right, very good. Oxygen is happy at 6, but we got 3 of them. So 6 times 3 is 18, and that minus sign, what will that tell you? Plus 1. Okay, so we got to put 24 valence electrons around the nitrate ion. Let's make nitrogen our central atom because I don't know which of the 3 oxygens is going to be center. Okay, so nitrogen. Okay, let's do this. 1, 2, 3. Okay. What do you think we should do here? Remember from our last lecture the oxygen. What will give an oxygen a minus formal charge? What will give oxygen a minus formal charge? Single bond or a double bond? Single. Okay. Single. And what's the charge here? Minus 1. So if you're good at this, you would actually do a double bond here, double bond here. This takes a little bit of practice, but you see now I have my minus formal charge. Right? So one little tool that you can use in your toolkit, especially in organic chemistry, the higher level chemistry. Okay, forget about all of this stuff. Okay, single bond oxygen, that will have a minus charge, minus formal charge. Double bond oxygen, forget about all the other stuff. Double bond oxygen, what will the charge be? 0. Okay, double bond oxygen 0. 1, 2, 3, 4, 5, 6, 7, 8. Perfect octet. Formal charge 1, 2, 3, 4, 5, 6. Oxygen happy at 6. 6 minus 6 is 0. Okay, so single bond oxygen, double bond oxygen. Okay, forget about everything else here. Single bond oxygen. 1, 2, 3, 4, 5, 6, 7, 8. Octet good. Single bond oxygen. 1, 2, 3, 4, 5, 6. 7. Oxygen happy at 6. 6 minus 7 is minus 1. All right, let's do formal charge for this nitrogen. 1, 2, 3, 4, 5. What is oxygen happy at? What is, let's do this again. I'm glad you guys are catching me. 1, 2, 3, 4, 5. What is nitrogen happy at? 5. Okay, 5 minus 5 is 0. Okay. Octet rule for this nitrogen. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, we call that an expanded octet, and that's fine. Okay, this is the best structure. Okay, if you do any other maneuvering, you're going to get formal charges here and there. Okay, this is the best structure. I already went over the oxygen here, but let's do it again. 1, 2, 3, 4, 5, 6, 7. Oxygen happy at what? 6. 6 minus 7 is minus 1. Octet rule for the single bonded oxygen. Count everything. 1, 2, 3, 4, 5, 6, 7, 8. The octet rule is satisfied for oxygen. Double bond oxygen. Okay, let's do this again. Okay, want to really get it coded in your DNA almost how this is going to be. 1, 2, 3, 4, 5, 6. Oxygen happy at what? 6. 6 minus 6 is 0. Okay, octet rule for this double bonded oxygen. Count with me. 1, 2, 3, 4, 5, 6, 7, and 8. Octet rule is satisfied. All right, so now, Josh, coming to you. You see I have the single bond here on the right hand. I could also have the single bond up top, right? So let's have the single bond up top. I'll move this pair of electrons here, kicking this one up to that oxygen. So this leftmost oxygen is untouched. And now the double bond is on the rightmost oxygen. And then one more, Joshua, and that is having my single bond left. Okay, single bond on left. Okay, don't forget your back and forth arrows. Okay, if I tell you to draw resonance structures, the bracket and the back and forth arrow, single bond on the left. And those are the 3 resonance structures of the nitrate ion. Okay, again, bringing your attention, let me highlight for you guys in pink the minus formal charges. Okay, do you guys see how they're delocalized? Okay, how they're sort of buzzing around the oxygens. Again, another example of delocalization. Delocalization. Let's do one more. Phosphate ion. Let's see if we can squeeze this in the last 2 or 3 minutes. Phosphate ion, nitrate ion, carbonate ion. Very, very stable, Zachary, because of these hybrid resonance structures. All right, what is phosphorus happy at? 5 is the right answer. What is oxygen happy at? Oxygen happy at 6, but you see we got 4 of them, so that's 24. Electrons, okay, plus 3. Everyone see that? Plus 3, gain 3 electrons. So our goal is to get 32 valence electrons around the phosphate ion. Okay, how will we do that? Okay, let's make phosphorus our central atom because we don't know whether oxygen 1, oxygen 2, oxygen 3, or oxygen 4 is center. We just don't know. And then we do 4 oxygens. Okay, what's our charge here, Zach? What's our charge? How do you think we'll get to -3? Have 1 double bond. Everyone see that? Okay, right? If this single bond is -1, this is -3, so yeah, have 1 double bond. Okay. Let's fill out the rest of our electrons. here's our -3. Here's our -1. Here's our -2. Here's our -3. Okay, don't forget we have 2 lone pairs on the double bond oxygen. Don't forget we have 2 lone pairs on the double bond oxygen. All right, on our last minute here, Zach, I'll pick on you. Where else can the double bond go? Yeah, so I'll have it on the top. I'm going to do this really fast. Okay, I'm having it at the top. Where else can I have it? The right, is that what you said? That's correct. Again, I'm going to do this really fast. And one more, Zachary. Right. Double bond here. You see how the double bond is delocalized? Okay, that's the word, delocalized. You said bottom, and you're, yeah, bottom. That's the resonance structure of the phosphate ion. Okay, the double bond. Okay, that -3, those -3 formal charges are buzzing around. They are buzzing around the 4 oxygen atoms. Okay, delocalization. It gives it very, very high amount of stability. All right, reminder of Friday, if you want to come, please come. If you can't make it, watch the video. And I will see you all on Friday. Happy Veterans Day. There is no class Wednesday. You did good, Zach. Felt like you're getting it.
Have a good day.
Thank you.
Yeah.
Where do you want me to sign it?
Just here. Thank you. You have a good rest of your day.
Thank you.